Assalamu alaikum. Welcome to the next lecture in this flexible AC transmission system. And in the previous lecture, as we know that we were discussing about the basics of Statcom. So today I will discuss about the power transfer from the input to the output in presence of the Statcom. Let us say we have this system in which a generating station is supplying to a node or a network through a transmission line whose reactance is x1 and x2, and in between x1 and x2 we are using a statcom. So you'll see that a statcom is a device that provides a constant current. We can assume that this statcom may be a constant current device. That's why I have used their IQ, and it is constant current in its operating range. So let us try to find the value of this statcom voltage in terms of this I1, V1 and X1. So you can see from here this V1 and statcom voltage are related by this voltage drop. That means when we subtract this voltage drop from this V1, so it will give us the statcom voltage. That's V statcom is equal to V1 minus J I1 X1. So these are all phasor forms. That means actually this had been V1 at an angle of delta. So using KCL at this point, I1 will be equal to the summation of these two currents, that's IQ plus I2. Now I will just try to find out this I1 in terms of these voltages and impedances. So by using the superposition principle, let us say this: if IQ is 0, this I1 will be equal to I2, then I2 will be equal to the voltage drop across these impedances divided by the impedance itself. So voltage drop will be equal to V1 minus V2, definitely to be a phasor difference, divided by the this reactance of the transmission line, that is J x1 plus x2. That means this I2 in absence of this will be equal to V1 minus V2 divided by J x1 plus x2. Similarly, this IQ will be equal to, let us suppress this voltage source and this load. That means it will be short circuited over here. You can see we have a current source in parallel to it are x1 and x2. So we need to find out this I2. So we can use the current divider rule. That means this I2 will be equal to IQ multiplied by x1, that is the opposite reactance, divided by x1 plus x2. So total current will be like this. That means I1 will be equal to V1 minus V2 divided by J x1 plus x2. This will be because of these two voltage sources. That will be this I2, and I2 because of this current source will be equal to IQ x2 divided by x1 plus x2. This is we have calculated by superposition. Now I will put the value of this I1 at this point. You can see that this V statcom is equal to V1 minus J. When you put over here the J, this J and J will cancel out. It will be minus I1 x1 into V1 minus V2 divided by x1 plus x2 plus. So when you multiply here J minus J x1 to this, it will be minus J IQ x1 x2 divided by x1 plus x2. So that's what this equation tells us. So let us say this quantity be equal to Vs. So when you simplify it, you will see that V1 x1 plus V2 x2 minus V1 x1 plus V2 x1. So this V1 x1 V1 x1 cancel out. This will be V1 x2 plus V2 x1 divided by x1 plus x2. This will be the value of the Vs. So the total statcom voltage will be then V statcom will be equal to Vs minus G IQ x1 x2 divided by x1 plus x2. This will remain as it is. This whole is as equal to V1. Now let us use this phasor diagram. So actually this is the phasor diagram that is drawn for this system. This is V2. Let's say this is V2, and we know that V1 is at an angle of delta to this V1. So you can say this is V1 at an angle of this, and this, when we connect this point and this point, it will have a voltage drop between these two. And definitely this voltage drop that we have made for this case, it will be without this statcom current, that is IQ. So this phasor diagram for this system is without this IQ. So let us say this point, that is the statcom point, is a point of C, A, O, B, C. This is a point C. Let us try to find out what will be the voltage OC, what will be its value. So first we'll calculate the voltage across the whole branch. That will be from here to here. It will be V1 minus V2. Definitely it will be the voltage drop between these two. So the voltage across this will be equal to V1 minus V2 divided by x1 plus x2. Simply voltage divider rule. V1 minus V2 will be the total voltage. The voltage across this will be equal to x1 divided by x1 plus x2. Or you can simply do it like this, since this is absent. The total current from here to here will be equal to V1 minus V2, that is this, divided by this jx1 plus x2 multiplied by the voltage across this will be equal to multiplied by jx1. That j and that j will cancel out. It will be equal to v1 minus v2 divided by x1 plus x2 into x1. So that is what we have calculated, that VAC will be the voltage drop across the x1, that will be equal to v1 minus v2 into x1 divided by x1 plus x2. So this will be VAC. Now we'll calculate the voltage drop VOC. You can see from here that this VOC, that is the point, this point, without the Statcom, it will be equal to V1 minus this voltage drop, that is this VOC minus this. That is what I have written over here. So VOC will be equal to VOA minus VAC. So VOA is the voltage V1 minus VOA minus VAC. VAC is this voltage. That means this will be equal to V1 minus V2 divided by x1 plus x2 into x1. And if you can just look at this equation, that is Vs, you will see this is the identical equation. That means Vs is actually equal to VOC. That means this voltage phase from point O to from point C is actually Vs. So that way we have derived it. Now when IQ is equal to 0, that until now we are discussing that, we will see this equation. When IQ is equal to 0, V Statcom is equal to Vs. So V Statcom is equal to VOC, that is equal to Vs. That means this voltage from this point to this point. It's very important, and we'll see that when IQ will not be equal to 0, what will happen to this voltage? It will definitely be different from this Vs. So it is different from this Vs by this term, that by this term, and we'll see where this term will lie. That we'll see in the and then I will come to this we can say this diagram. From this phasor diagram you can see that this Vs is equal to Vs at an angle of delta minus alpha with respect to this reference, that is voltage phasor V2. So the angle of V1 with respect to V2 is delta. The angle of V1 with respect to Vs, let us say it is alpha. So the angle of this Vs with respect to this will be equal to delta minus alpha. That's what I have written over here. Now when the Statcom should act as a capacitor, that means it should draw a current. It should draw a current IQ, which should be leading to this Vs by 90 degrees. That means the angle of this IQ should be equal to 90 plus delta minus alpha, because the angle of Vs will be delta plus alpha with respect to this. So its angle will be 90 degrees with respect to this. That means the angle of this IQ with respect to this will be equal to 90 plus delta minus alpha. So with this it is okay. So how can we actually get this? You can see this IQ can be replaced by this J. This is the magnitude of IQ only. J means the introduction of this angle, that is 90 degrees. And what is the Vs phasor divided by magnitude of Vs? You can see from here, Vs phasor divided by magnitude of Vs will be equal to 1 angle delta minus alpha. That means this will take care of the whole angle. So actually this IQ will be equal to same IQ, angle of 90 minus delta minus alpha. That actually this is usually used in control strategies to derive the angle of this IQ with respect to Vs. So here we also derived it, and will be using this equation in equation 2, that is this equation, to derive the real power that is drawn by the Statcom or supplied by the Statcom. So when this IQ is replaced by this IQ Vs by Vs, so J into minus J is minus J square, that will be plus 1, it will be plus. So IQ will remain is this. Here IQ is a phasor, this IQ, but when you put it over here, it will be simply a magnitude. then Vs by Vs, Vs by Vs is as it is, and then x1 x2 divided by x1 plus x2, they are also as it is. So our equation will be reduced to this equation. So we can take Vs phasor to common from this equation. It will be equal to 1 Vs into 1 plus iq divided by Vs into x1 plus x2, x1 into x2 divided by x1 plus x2. So that is what we have the final equation. Now you can see this is all these things are in magnitude and Vs is the phasor. That means this V Statcom is equal to Vs and some extra term which is again in phase with Vs. So that means V Statcom will be this voltage, that is from O to, let us say this is point E, OE, which is greater than Vs. So it will be again in the direction of the Vs. That is what I have, that's why I have drawn this Vs and I have extended it to V Statcom. This will be the Statcom voltage when IQ is not equal to 0. So there may be some other term, for example, if it has to act as an inductor, in that case this where is that, this IQ has to be lagging to this voltage by 90 degrees. It should be in the downward direction. That means here we have to use a minus j IQ Vs by Vs. When that is the case, you will see that this V Statcom will be less than Vs. It will be in this direction. V Statcom will be at this line towards the left side of this line. So V Statcom will be only from this point to this point. In that case, it will be less and it will be drawing the reactive power. But since we assume it to be a capacitor, it will increase the it will supply the reactive power. Now from this triangle, that is from triangle A, B and C, we'll use the sine law of angles, that is equal to the ratio of the angle, sine of angle to the side opposite to that of angle. All the ratios of the angles to the side opposite to the angle are equal to each other. That means sine of beta divided by the opposite side, that is BC, which is V2. Sine of beta by V2 is equal to sine of delta divided by this whole, that is V1 minus V2. Will be equal. That means sine of beta into V1 minus V2 is equal to V2 sine of delta. Now in this smaller triangle A, B and D, sine of alpha divided by this VAD, that is this voltage drop, that is equal to V1 minus V2 into x1 divided by x1 plus x2, that is this, is equal to sine of beta divided by Vs. Now the opposite side will be this, because the triangle is A, B and D. So it will be equal to sine of alpha into sine of beta divided by Vs, that is this, multiplied by V1 minus V2 into x1 divided by x1 plus x2. Now from this equation, sine of beta into V1 minus V2 is equal to V2 sine of delta, that is sine of alpha is equal to V2 sine of delta in place of this, divided by Vs into x1 divided by x1 plus x2. This is sine of alpha. So now this is what we have discussed just now. Now P is equal to, that is the power transfer that takes place between input and the Statcom. You can see it from this diagram. That will be this voltage multiplied by this voltage divided by this reactance, and sine of angle between V1 and V Statcom. Since sine of between V1 and V Statcom is this alpha, that will be equal to V1 V Statcom divided by x1 into sine of alpha. That is the power transfer between input voltage and the Statcom. So that is what we have done over here. So to get the actual power, we have to replace this V Statcom and sine alpha. So I will write it like this: V1 by x1 sine of alpha into V Statcom. So V1 by x1 is as it is. So sine alpha is this, V2 by Vs, sine of delta x1 divided by x1 plus x2, x1 divided by x1 plus x2 into V Statcom as it is. So x1 and x1 will cancel out. So it will be equal to V1 V2 sine of delta divided by x1 plus x2 into V Statcom divided by Vs. That is here. Now from this equation, you can see from this equation, V Statcom by Vs will be equal to 1 plus IQ by Vs into x1 x2 divided by x1 plus x2. So I will replace it by this equation. So the equation for real power will be equal to V1 V2 by x1 plus x2 sine of delta into 1 plus IQ divided by magnitude of Vs into x1 x2 divided by x1 plus x2. So from the earlier equations, perhaps this is the equation 1. Yes, this is the equation 1. The Vs phasor will be equal to V1 x1 plus V2 x1 in terms of phasors divided by x1 plus x2. So when you get the magnitude of it, so when you add two phasors or two vectors, let's say A or B, that will be equal to square root of a square plus b square plus 2ab cos of theta, where theta will be the angle between a and b. Similarly, this will be equal to magnitude of vs will be equal to square root of v1 square x1 square plus v2 square plus v2 square into x1 square plus twice v1 v2 x1 x2 cos of, that is angle between v1 and v2. Angle between v1 and v2 is delta, that is cos of delta. So that is what I have written over here. You can see v1 square x1 square plus v2 square x2 square plus twice v1 x1 v2 x2 cos of delta divided by x1 plus x2. So when you multiply this x1 plus x2 to this vs, it will be equal to vs into x1 plus x2 multiply is equal to this term. So here also, since in the denominator we have this multiplication, these two terms, that is vs into x1 plus x2, it will be this term, that is square root of x1 square v1 square v2 square plus v2 square into x2 square plus twice v1 v2 x1 x2 cos of delta. So the equation is reduced to this, that is I1 x1 x2 iq x1 x2, yes, v1 v2 sin of delta divided by x1 plus x2 into 1 plus iq x1 x2 whole divided by v1 square x2 square plus v2 square x1 square plus twice v1 x1 x v1 x v2 x1 x2 cos of delta. Now, as you will always see that we have usually two machine model where v1 is equal to v2, that is, let us say, equal to v, and we usually use this compensator at the middle of the line. That means x1 is equal to x2 is equal to x by 2. So when that is the case, this v1 and v2 will be equal to v square, x1 plus x2 will be equal to x. So it will be equal to v square by x sin of delta. This is one is as it is. X1 into x2 will be equal to x square by 4. v1 square is v square. x2 square will be equal to x square by 4. So v square into x square by 4. This will be again v1 v2 will be twice v square, and x1 x2 will be equal to x square by 4 cos of delta. So I will take from the every term, there are three terms. We have v square x square by 4, which is common. I will take it outside the root. It will be equal to vx by 4, and vx by 2, sorry, x by 2 in the denominator, and 1 x by 2 from here will be cancelled out. It remains x by 2 only. So it will be equal to iq x by 2 divided by v 2. It will be equal to 1 plus 2 cos of delta, that is 2 plus cos of delta, that is this. Now I have reached over here. It will be equal to iq cos of iq x by 2 into v, taking 2 as a common, it will be equal to 2 plus 1 plus cos of delta. So 1 plus cos of delta into this into half angle formula will be equal to twice cos square delta by 2. So when you multiply it by 2, it will be equal to 4 times cos square delta by 2. The square root of 4 times cos square delta by 2 will be only 2 times cos of delta by 2. So our equation will be written as v square sin delta by x into 1 plus iq x by 2 divided by v into 2 cos of delta by 2. Now taking the sin delta inside, it will be equal to v square by x sin of delta plus iq x by 2 as it is, twice v as it is. In the numerator, it will be equal to twice sin delta by 2 cos delta by 2, and in the denominator we have cos delta by 2. This cos delta by 2 and this cos delta by 2 will cancel out. This 2 and 2 will cancel out. It will be equal to iq into this x divided by this 2 into v and this sin of delta by 2. So this is our final relation. So for different iq's, I have drawn the p delta curve. For iq is equal to 0, this is iq is equal to 0. There will be a normal uncompensated line, that is p max sin of delta. This will not be the term. This is for that case iq is equal to 0. When iq is equal to, let us say, 0.5, iq is equal to 1, it is given, it is like this. This iq is equal to 1, it will be upwards everywhere because it will be adding some term to it which is positive. And this point is pi. iq is equal to 0, at pi is equal to delta is equal to pi, this will be equal to 0. So this is pi. At pi, for every value of the pi, this term will be 0, but this term will have some value, because sin pi, this will be maximum value iq x by 2, that will be at this point. Similarly, for iq is equal to 1.5, it will again increase like this, but it will go beyond the pi. So usually we restrict this value of pi to delta to pi. So if we draw a line over here, so I will have one line over here, iq is equal to 0, one line over here, iq is equal to 0.5, to go up to this pi, and one curve over here is equal to iq is equal to 1.5. When iq is equal to minus 0.5, in that case, it will have a less peak and it will go to 0 beyond this. before reaching to the wire. This is the variation of this IQ, or we can say P with respect to delta for different IQ. That is the injected current by the Statcom. So we'll be always using this formula to calculate the real power transfer in presence of the we can say the Statcom. So actually the Statcom is also a non-ideal device. In case of ideal device, we were having this curve going from this point to this one like this at pi. So it will not have any decreasing value, but here it has definitely increased the power transfer, but it will be having some decreasing value. That means that stability problems will also be there, even if it is less, but it will also be there. Now let us see the VI characters, which is the important parameter of the Statcom. So there are two VI characteristics that is shown in the figure. A typical VI characteristic of a Statcom is depicted in the figure shown below. This is the VI characteristic of a Statcom of an ideal Statcom. This is the VI characteristics of the practical Statcom. In this case, we have a slope that we already know why here we have a slope. So from this point to this point, first we'll discuss about the ideal. From this point to this point, even if what will be the system voltage, you will see that always it will draw the maximum capacitive current here. From here to here, if the system voltage increases, whatever be the voltage, it will draw the same amount of maximum current, inductive current. So in earlier case, it was dependent upon the value of this reactive power, how much reactive power we have to draw, how much is the system voltage. As per that voltage, this reactive current, or you can say this capacitive current, will be drawn. But here, for an ideal case, it is independent of the voltage. If the voltage is very less, it will draw this much of the current, and it will provide the actual value of the reactive power that is needed to make the system voltage equal to the reference voltage. These lines actually mark the different reference voltages. This is the voltage limit, that is this Vmax. Imax is the current limit. Imax is the current limit on this side. On this side, maybe it may be same on both the sides. So the Statcom can supply both a capacitive and inductive compensation, and is able to independently control its output current over the rated maximum capacitive or inductive range, irrespective of the amount of AC system voltage. It does not depend upon the voltage. So that is its you can say the strongest feature. The Statcom can provide full capacitive reactive power at any system voltage. It is able to supply its full capacitive power at any rated voltage, even as low as 0.15 for the practical case. You can see from here to here 0.15 per unit of the voltage. At this point of it is able to supply the maximum reactive power that it is capable of. That is why it is very superior to the normal, or you can say other shunt compensators. From here to here, it will not be able to do that, because it will again act as a capacitor from this point to this point. Because it is a practical case, so it also has some lower limitation and upper limitation, or lower limits and upper limits. The characteristics of the Statcom reveals another strength of the technology, that it is capable of yielding a full output capacitive generation almost independent of the system voltage, constant current output at lower voltage. You can see at every voltage here, and from this point to this point, it is a constant current source independent of the system voltage. That is why we have already modeled it as a constant current source in the derivation of the power as well. This capability is particularly used for situations in which the Statcom is needed to support the system voltage during and after faults, where voltage collapse would otherwise be a limiting factor. Because since it is capable of supplying the maximum reactive power even at the voltage as low as 0.15 per unit, so during the faults the voltage may go to that value as well, so it is able to supply the reactive power in that range as well. So it is again its advantage using the Statcom in that range as well. Now we may use some hybrid Var generators. We have a capacitor, we have a Statcom, so it will try to we can say extend its limits towards the capacitive side, because you will see that if this is the Statcom, this one and this one is the Statcom VI characteristics. So by having different voltages, since capacitor current depends upon the system voltage, and let us say the voltage is less, you will see that this current go on decreasing at this point. The current that is drawn by this capacitor will be maximum, so the total capacitive current will be this much from this point to this point. And as voltage decreases, you can see that for an ideal case of the Statcom, here also it will be equal to the maximum value of the Statcom current only. There will be no capacitor current. In inductive range, since it will act as the inductor, this capacitor current will cancel out this I Statcom current, so it will only act from this point to this point. So that is how the combination of these two work. Similarly for inductive case, so in that case inductive current will be added and it will be subtracted in the capacitive region, and again this inductive current is dependent on the system voltage. As system voltage increases, inductive current also increases. As system voltage decreases, inductive current will decrease. You can see from here. Here Statcom will act as a in this range it will act as a capacitor, so it will draw the constant maximum current of this, and inductor will also draw the always draw the inductor current. It will be subtracted over here. Here it will be added to this inductive current of the Statcom. So here it is for both the cases. So capacitive range, because this will act only when the system voltage is less and in this region only, so it will extend its range up from this point to this point. So inductor will act only in this range, so this will act this will extend its range from this point to this point. So the total current in inductive range will be equal to Statcom current plus ITCR. Here total current in this capacitive current will be equal to I Statcom maximum plus ITSC. So I think I will stop over here. I will discuss this comparison of Statcom and SVC in the next class.